the longitudinal aerodynamic forces and moments. So we're filling in the different columns of this matrix. That's the perturbed forces. And the way we're doing this is we're writing an expression for the full force and moment, or moment, and then we take the derivative with respect to the perturbation variable, which gives us the derivatives that go in these models. So this is a derivative, and we multiply it by u. So this is dfx by du, and then we multiply by u to get the value. So we've already done this column. We've done this column. So now we're getting ready to start on the alpha dot perturbations. So the alpha dot is the lag effect of the downwash, how long it takes to get to the tail. So the non-dimensional version of this is alpha dot c bar over 2u1. And this, we defined this a couple days ago. And this is called a reduced frequency. Sometimes it's called K, lowercase k. Typically in flight dynamics, people call this alpha dot hat, so that you know it's not alpha dot, it's this combination of variables. It's used in aeroelasticity. And it's called the Strohel number. And aeroelasticity has to do with oscillating airfoils. So that's why this shows up there, is that when an airfoil or a wing is oscillating an angle of attack, you have an alpha dot. And so they'll model that behavior like that. And so along with what we do with this lag in the downwash model is we make an assumption that it's this reduced frequency is less than about 0.04, which means that we don't have to include the full effect of an oscillating airfoil. All we have to do is include the lag of the downwash getting back to the tail. If you have an oscillating airfoil, and you look at its lift versus angle of attack, the curves that we're used to seeing are a straight line up and a stall, and that's really a steady state lift. You put it in the wind tunnel at a certain alpha, you leave it at that alpha for a long time, and then you read the steady state lift. If the airfoil is oscillating, that is, alpha is varying, say, plus or minus 1 degree, you actually get a curve that looks like this. On the upslope, when alpha is increasing, it follows this curve. But then when it starts pitching back down, there's a lag in the flow developing over the wing, and you get this curve. So it comes back on the downstroke to that value, and then if you go back up, then it goes back up like that. So that's an extra effect that we're not talking about. We're just talking about the lag of the downwash. So that's our model. So the idea is that the downwash comes from the vortex, the trailing vortex, yeah. Any airfoil. If it's oscillating, it's pitching up and down. So, right, if you have flutter, the wingtip is fluttering up and down in pitch, and so you get this behavior. So the idea is that the downwash takes a certain amount of time. It's developed on the wing. So if you change the angle of attack, it takes the distance from the wing to the tail for that effect to be felt by the tail. And so that's the key factor, is the distance from the wing to the tail. We'll call that XH. That's our moment arm from the CG back to the tail. So that's a pretty good measure. The distance from the wing to the tail, XH, creates a lag. In the downwash at the tail. And that lag, delta T, is just the time that it takes for the flow going at a velocity U1 to go the distance XH. Oh, I'd have to divide. I knew something was wrong there. Because if you take U1 times time, you get distance, velocity times time. So what that means is we're going to say that the downwash at time t depends on the angle of attack of the wing delta t seconds ago, because it took that long for it to get there. So the downwash we're seeing at the tail actually was generated by the wing delta t seconds ago. And so we use this in our downwash model. So our downwash model looks like this. So it depends on the angle of attack at that time ago, and then we use a Taylor series. To expand a function at a distance delta t away from its base function. So the Taylor series says that, well, you can shoot from time t backward a distance delta t times its slope. So really all we're saying is that if we have some function f of x and its curve looks like this, so if you're at the value x and you want to know the value at x plus delta x, you just do the slope up to that point. So you do the slope at x, shoot up to the x plus delta x, and that's all this formula is saying, is you use the value, and then you just slope up at this slope times the distance. We're actually going backward in the delta t. So there's the alpha dot effect. Oh, well, this is not right. it's d alpha dt because it's the function. So there's the alpha dot effect. And that's why it's called an alpha dot effect. Of course, there's other terms for this Taylor series. If you go back and study the Taylor series, you can include the second derivative and the squared term, which means you're doing a parabolic curve fit instead of a line curve fit. And you keep going. But we say these are small. So that's what ties into that k being a small number, is if alpha dot is small enough, then the second derivative is not so big. So if we go up here, that's how epsilon, the downwash, depends upon alpha dot. So that's the effect we're looking for. And I've used our delta t as xh over u1, so I've substituted that in. So this is our downwash model, including the lag. And so we have to include that in our lift model and our drag model, and so on. So originally, when people were developing forces and moment models, they probably didn't include this. And then they found out, well, their numbers that they were predicting didn't match experiment. Where's the difference? And they found out that this effect was there. So now we go back, and we're going to use this in finding out the effect on the drag and the lift and the pitching moment due to alpha dot, because the alpha dot effect is exactly this thing here. So now we go back to what we've been doing. We write an expression for the x force aerodynamic, and we're going to see, well, how does it change with this non-dimensionalized alpha dot? And we know it does now because there's alpha dot in the downwash. So go back, and the drag model, remember, has some drag in it, but it also has a small component of lift. So we look in there and say, well, what varies with alpha dot? CD does, CL does, alpha does not. This is alpha dot, not alpha. And so this alpha is a small term compared to CD, so we're going to say that this term we can say is small. Especially since when we're done, we're going to take this and multiply it times alpha dot, and that's the product of two small terms. And so this one's easy. We're just going to say, okay, we just need to figure out what the drag derivative is with respect to alpha dot. Remembering that when you see this, we don't take CD. This does not mean, so cross that off. That's not right. This means the derivative of CD with respect to alpha dot C bar over 2U1, and we just have to remember that. The table, that matrix that I showed you, makes it obvious because it lists out the alpha dot C bar over 2U1 in that right-hand column of the vector. There's not a whole lot more we can do this unless we have a really good drag model. And the textbook says that this tends to be small. So we can, for a preliminary design, kind of neglect this. But it does happen because the drag is going to depend upon alpha dot because the induced drag of the horizontal tail depends upon this, the lift of the horizontal tail, which depends upon alpha dot. But the lift effect is a bigger effect. I'm going to save this because we need this for the lift here. So we're going to repeat this same thing, only for the Z force. And so that has mostly lift, but a little bit of drag component because of that tilting of the relative wind with the perturbation of alpha. But again, we can say, okay, here's alpha, it's small, it's going to be multiplied by alpha dot, so we can say this is small. So again, this is easy. Except because we know the lift model, we can come up with a better formula than just saying, oh, well, we need to know CL alpha dot. So that's what I'm going to walk through next. Because we know that the lift comes from the wing and the horizontal tail. And then we look at this and we go, well, the downwash only really affects the horizontal tail, so we knock out the wing part. And then we can predict the lift of the horizontal tail because we take CL alpha times alpha. So we're going to build up CL of the horizontal tail. Now remember this, because eventually we're going to get epsilon in the angle of attack of the horizontal tail, and so we're going to have to substitute that in. All right, so here's how it works. CL of the whole airplane is the wing part plus the horizontal tail part. And in fact, we did this way back early in chapter 3 when we were developing our lift model for the airplane, right? And then we said, well, CL of the wing is its lift curve slope times its angle of attack. And then CL of the horizontal tail is its lift curve slope times its angle of attack. But we know that alpha dot is not in here because we've already said, well, it's a horizontal tail lag effect, right? So the wing is not really affected by this lag. And that's an assumption because if you have alpha dot going fast enough, I showed you that hysteresis, the lift curve slope. If you're really oscillating, then you got to include this effect in the wing as well. So alpha dot is here. So we can say, hey, we found it. So what's CLH? Well, it's the lift curve slope. CL subscript alpha of the horizontal tail. So that's the lift curve slope that in 514 we used the big formula for to calculate the lift curve slope of that thing, right? And then we multiply it by the angle of attack, which is a big complicated thing because it's the angle of attack of the airplane plus however much we've tilted the horizontal tail up minus the downwash. And here's where we use our model. And then we go, aha, I knew alpha dot was in this somewhere. There it is, right there. So what this says is we need to take the derivative of CL with respect to that weird combination of variables. And CL depends on CLH, and CLH depends on alpha dot, so that's where it all comes from. So I just picked out the part that has alpha dot in it. And now we just take the derivative of this thing with respect to that weird combination. And again, we can turn this into just a derivative with respect to alpha dot. This comes outside and flips up. And there's alpha dot. So really, we don't get anything from here, 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 or here, because alpha dot's only here. And so we get this stuff. Goes up here for the derivative. So I want to write this out carefully. So we got the 2u1 over c bar that came from the non-dimensional alpha dot, right? It came from the fact that we decided to non-dimensionalize it. And then we got this derivative, so let's throw in the a to h, sh over s, and then we get all this stuff in here. I think I got everything. And here's a big deal. You go, what do you mean a big deal? Notice that there's a U1 here, and the U1 here that cancel out. Well, that's nice, but it's a bigger deal than that. Where did this U1 come from? Came from over here. Where did XH over U1 come from? Look back on the previous page. Where did that come from? Yeah, that came from the delta T, so that's the lag. So there's our lag and downwash model, and that's how the alpha dot effect came into play, is that lag, right? Okay, so then where did this U1 come from? Because it's really nice that it's there and we can cancel out U1, right? It came because we non-dimensionalized up here. Okay, so that's nice, but why is it such a big deal? It's because, let's say that we didn't non-dimensionalize. Then our term that's going to go into that matrix, the CL subscript alpha dot, would depend upon velocity, which means every different airspeed we flew our airplane, we'd have to recalculate that number to plug into the matrix. That'd be a pain, wouldn't it? Okay, I want to do my analysis at 100 knots. Okay, recalculate CL alpha dot. Now I want to find it 200 knots. Well, okay, recalculate CL alpha dot for every velocity. So this non-dimensionalization is similar to why we define CL as lift over 1/2 rho d squared s, is because it takes out the velocity dependence. It also takes out the dependence on density and area of the lift. So you don't have to recalculate or relook up your lift every time you're flying at a different velocity. Same deal here. So we do get that term knocked out. So that cancels out, and it gives us a nice formula that we can calculate one time for the airplane, and it's good for pretty much any flight speed. Now, it will change a little bit with flight speed, but it's pretty much constant. So it's nice that way. So this is a good reason to do this non-dimensional variable thing. All right, so that gives us that term in the matrix. And that's pretty complicated because this is not a known effect that we've known about before, and it takes a lot of time to figure out, well, what the heck, why do we include alpha dot? So you might be thinking, oh no, now we got to do CM alpha dot, right? Same story over and over again. But it's actually easy because we've already done the hard work. So the CM total of the airplane is CM of the wing plus CM of the horizontal tail. But the nice thing is the pitching moment caused by the horizontal tail can be easily calculated from the lift of the horizontal tail. In fact, that's how we did it, is we added the lift of the pitching moment of the wing, and then we just took the lift of the horizontal tail and multiplied it by the moment arm, and we were good. So that means that this effect is only in here. And so the CM of the horizontal tail can be calculated from the lift of the horizontal tail times XH over C bar, because we non-dimensionalize it. We need to remember to put a minus sign here because the lift of the horizontal tail being behind the CG causes a negative nose-down pitching moment. But because we're smart enough and lazy enough that we look back and go, oh, it's easy to calculate CMH from the lift, and we've already done the lift, so we're done. Because the derivative of this is, sorry, this should be CLH. And we've already done the derivative of this thing with respect to alpha dot. So all we have to do is take this formula and multiply this, and we're good. And so that's the formula in your book that it points to in that matrix for calculating CM alpha dot. So I just use this formula in here. So I want you to understand two sides of this. One, the derivation and how the alpha dot shows up in the lag and the downwash, and how you get epsilon at t depends upon alpha at time t, delta t later, and how you deal with that, and that shows the alpha dot. But I also want you to understand and be able to explain this like to your grandmother. I'll say that a lot because that's important. Because you may end up having to explain this effect to your boss who hasn't been in school for 20 years and may not even have a degree in aerospace engineering. I mean, you'll be a technical engineer guy. And you'll impress him if you can give him an explanation that doesn't include 2 pages of equations, right? So what would you say? Go back to the fundamental explanation that I said, is that this is an effect of the time it takes the wake vortex to get back to the tail. And that's why we get the time dependence on angle of attack, right? So that's the explanation that you'd say. And if I ask that on a quiz or a test, I may ask for the derivation, but I'm more likely to ask for that simple explanation, is explain the alpha dot effect. Where does it come from? And that's what you'd put down. All right, so we got the next column in that thing. Totally, that's, yeah, the word lag means falling behind, right? If you're lagging somebody in a race, you're a time delta t behind them. So it's the delta t time it takes for the downwash change at the wing to get to the tail. So now we've done this column. Oh, make sure when you look at your book that those dots on those terms are real obvious. In fact, I recommend that you take a pen and make sure that that dot shows up on this formula. Because on some books, it's kind of faint. And I've had students on an exam or on homework not see the dot because it's faint in their book. So if you don't have your book with you, write in big letters, equation 3.162, page 147. Put a dot on the alpha where it's supposed to be. Obviously, don't put a dot on this one. So the next term we're going to do is CDQ, CLQ, CMQ. So this is the effect of pitch rate on lift, drag, and pitching moment. So I brought the foam airplane of flight dynamics because this is nice for visualizing some of these effects. I'm not on screen. If we were doing these video lectures right, it'd be like a talk show. We'd have the guy with the cue cards out here so I'd remember what I'm supposed to say, right? We have the cameraman, the production staff, and then we'd have the guy that sits in the corner and laughs whenever I make a joke. And then I'd have the band over here that played an intro to the class. That'd be kind of cool, right? But then this class would probably cost you like $10,000 instead of, unless we put advertisements on it. Okay, so here we're talking about the pitch rate and the effect on the lift, drag, and pitching moment. So remember we got flow coming in this way, right? And now we're talking about an airplane pitching, so nose up is positive pitch. So we're talking about an airplane spinning slowly, because we're not talking about fast spins, spinning like this. So the CG is pretty much near the center of the wing, right? So the wing is rotating, but what do you see sweeping through the air pretty quickly? This thing, right? See how it's sweeping down? There's air coming this way, right? So I'm exaggerating this. But as this sweeps down, it creates a relative wind from below in addition to the forward speed, and so it's increasing the angle of attack of the horizontal tail due to the pitch rate. It already has an angle of attack due to everything else. And so that's the added thing we need to add into the formula for the lift and the drag and the pitching moment. Now, looking at this, as we're pitching positive, is the pitching moment due to the cue stopping this motion or making it more. So now I'm talking more stability. So which way? We're increasing the angle of attack, right? So the relative, when it's coming this way, what's it going to do? It's going to stop the motion, right? And that's a good thing. In fact, what it's doing is it's damping this motion. Just like when you have a mass spring damper system, the damper in there slows down the velocity of the mass. If you take the damper away, it bounces back and forth forever because the spring compresses. You just get a trade-off of kinetic and potential. There's no dissipation. So this effect that we're going to be talking about now is a pitch damping term. And it will be really important when we solve the differential equations for damping out the motion of a pitch disturbance and a pitch rate disturbance. All right, and while we have the foam airplane, that lag in the downwash, we could talk about that. I've drawn pictures, but you've got the flow coming through like this. If you rapidly pitch the airplane up, the angle of attack of the wing changes, right? So the lift changes and the pressure distribution changes, but it takes a while for that wingtip vortex to get back here, and that's the lag. The change in the vortex from that sudden pitch up. And my glider is not real structurally sound, is it? All right, so we're going to look at the change in the drag and the pitching moment and the lift due to that pitch rate. And we'll draw exactly that picture, and it's going to depend upon how far the tail is behind the CG, because that's going to determine how fast that's moving through. The further it is out on the radius of the circular motion, the faster it goes down and the bigger the change in angle of attack. And we consider this a perturbation on steady state level flight cruise condition because when we're cruising, we have no pitch rate. And we have this non-dimensional pitch rate. So this is another reduced frequency. And here's our big picture of what the airplane was doing. Here's the wing. There's the CG. We have a positive pitch rate nose up about the CG. Is what? I'm sorry. There's not. What you're seeing is an illusion or a mistake. Yeah, thank you. Because otherwise it looks like dynamic pressure, which is totally wrong. Thank you. Okay, so then here's the horizontal tail, and its aerodynamic center is here, which is where the lift acts. And so how fast that thing is sweeping downward is xh times q. Radius times rate per time gives the downward velocity. And so we get a delta vertical velocity that's q times xh, and that's how q gets into the formula, because that's an increase in angle of attack that produces CL. So the change in angle of attack of the horizontal tail just due to the pitch rate is that delta W divided by the forward speed, because that's how we calculate an angle of attack. It's the forward component of the velocity, tangent the vertical, or sine. You get tangent the vertical component, but then we say that it's small, so the tangent's equal to the angle. So that's the change in angle of attack that gives us a change in lift. So we're going to need this in a minute because we're going to do the drag, lift, and pitching moment. The drag's easy because we don't have a good linear model of the drag versus angle of attack, so we'll just say, well, we'll calculate it using some formulas or wind tunnel tests. So we're taking the derivative of our normal formula for FAX. And again, we're going to say this is small because alpha is small. And so we just get the derivative of CD with respect to this thing. And since we can't really go any further than this, we'll just call it CDQ and say, well, we need some kind of wind tunnel data that tells us what that is. And there are wind tunnels where you spin your model and it gives you these derivatives. And this tends to be small. If you remember back in the matrix, he put a wiggly equal sign and said, well, this is pretty small. Because the drag of the tail is a lot smaller than the drag of the wing, and this is the only effect. Okay, so how about, oh, let's see. This is FAX. So then how about the lift direction? Oh, I botched that totally up. We're taking the derivative of this thing, which is, I apologize, I got ahead of the game here. So we're doing FAX. It's the derivative of that thing because that's FAX. And now we do the same thing in the Z direction. And again, this second term is small. In fact, remember the only time that term we actually kept is when it multiplied the derivative of Q bar with respect to whatever. Another word of caution when you see CD subscript Q, it doesn't mean the derivative of CD with respect to Q. It means with respect to that whole deal of non-dimensional variable. So you just have to remember that. And it turns out if you forget this, and let's say you take this and you just multiply by Q in the formula, turns out you get a way bigger effect than it really should be, because here you're dividing by U1, which is a big number. And we actually, a long time ago, developed a MATLAB model for an airplane and forgot to do that, and we're getting crazy high forces, and it's because of that. We forgot to do Q times C bar over 2U1. Now, because we have a good lift model, we can go a little bit further than this. Same thing that we just went through for alpha dot, except now we're talking about Q, but Q affects only the lift of the horizontal tail, just like alpha dot affected only the horizontal tail. So that's how we do the same story, is we just write the formula for CLH. And it's going to be the lift curve slope for that thing times the angle of attack of the horizontal tail and the extra angle of attack that we just derived. So this is alpha plus IH minus downwash. None of that we care about, because all we care about now is how that changed with respect to Q. And so there's the Q effect right there. Because when we go through and take the derivative of CL with respect to Q, C bar over 2U1, we end up with 2U1 over C bar, the derivative with respect to Q, and all we care about is that. And we've got to carry the ADH SH over S. And so the derivative with respect to Q is going to knock out that Q there and leave us just with what's left. And again, we get the nice thing happening where the U goes away. So the U cancels out. And this derivative is not going to depend upon forward speed. And so we're saying the Q effect only affects the horizontal tail, right? And so there's the formula for that. So this is nice because we know all this stuff. If we design an airplane, we know SH and S and all this other stuff. We know the lift curve slope of our horizontal tail, so we can get a pretty good estimate of this derivative. The drag, not so much, but then we can say it's kind of small. Yeah. Like this? Yeah, that's all in here, right? So if we wrote alpha H, that's alpha plus IH minus epsilon 0 minus D epsilon D alpha. Is this showing on the screen, by the way? Right, so that all goes in there. Oh, and there's the alpha dot that I didn't even write. So why do we ignore that? It's because there's no Q. So we have to put it in here, but then when we take the derivative, I suppose I should have written it all in here because I didn't take the derivative, but all that stuff is constant with respect to Q. So let's write other stuff, not depending on Q. That's a good question because I kind of shortcutted that. So the formula for CLQ is that. And then we can do the same trick that we did for the pitching moment. Because the pitching moment, again, depends upon the lift of the tail ratioed by the moment arm back to the tail. So the formula for CLQ looks like this. Yeah, we got the XH over C bar goes there, so we're good. Then the formula for CMQ is ratioed by the moment arm. So we actually get 2 XHs over C bars. And because of the direction of the pitching moment, again, it's negative if we have a positive CL. So if you look this formula up in the book, instead of a 2 here, as a 2.2. So you look at that and you go, where'd the 0.2 come from? Well, it turns out that from experience in wind tunnel tests, that when the airplane is pitching, center of gravity is like right here, you get a little bit of wing effect because it's rotating as well. And so that 0.2 is a fudge factor that fits experimental data. You like that? So they just arbitrarily, not arbitrarily, but based on experiment, the little bit of wing effect adds that extra 0.2 for most airplanes. Now, if you want to do better than that, you've got to do a full analysis of the lift distribution on the wing and how it changes when you pitch the wing, and that gets more complicated. So preliminary design, real quick calculations, you use that, and then you validate your numbers either with CFD or in wind tunnels. Again, we're engineers, so when you're doing a preliminary design, you don't want a real complicated analysis of every airplane design you're looking at. You want a quick analysis to see, well, what is more viable to explore in more depth. So all these formulas are in the book. Again, I won't expect you to memorize them. I do want you to know the effect and be able to explain it. So I might ask you to draw a picture just like I did and say, well, if you have a positive Q, the tail's moving down, which increases the angle of attack of the tail, and that angle of attack change depends upon Q and the distance back to it, right? How are we doing on time? 5:04. Time for a paid political ad. No, I'm kidding. But well, heads up, I went over and voted at Coke Arena at 1 o'clock this afternoon, and there was no wait. So you can advance vote over there if you want to. I'd heard there were long lines in other places, so I was skeptical, but I went over there. And not only that, but you get to vote where the Shockers play basketball, for what that's worth. What? You have to let them know your time or something? No, I just walked in. You walk in, you show your driver's license, they scan it, you pop up in your picture, and they validate you and you vote. So it's real slick. So back to the matrix. I should apply? No, I just thought, well, that was, you know, sometimes they've talked about people waiting in line forever to vote. And yeah, yeah. Let's see, so we're back to the matrix here. So we just did this column here. And again, if you're using this, it reminds you that you have to multiply by Q C bar over 2U1. The next column is real easy, because notice this is just the derivatives of CD, CL, and CM with respect to elevator, and we've done those already when we did the steady state forces and moments. So it's just the lift curve slope times the effective effect, that doesn't make sense, of the elevator on the lift. So going through the formal procedure we've been doing, again, we don't want to do the derivative of this with respect to the elevator, and we're talking about a perturbation. So the elevator is already trimmed at like -2 degrees. Then we're going to go just a little like -2.1 as perturbation. But this still, oh, I'm not, thank you. That's where I need the producer for my talk show here. So this is easy because we're just talking about the derivative of Oh, okay, we're down here. FAX, right? Okay, I got that. And we say, well, what is deflecting the elevator effect? Well, it could change the drag. It could also change the lift, but that change would be multiplied by another small number, so we say that's small. So we just write this as, and we already did this. That's just, well, what is the change in drag with respect to a little bit of an elevator deflection? And so the lift is the same exact formulation. We end up with minus CL delta E Q bar S. And then the pitching moment you just get the derivative. And we look at this and we see a plus sign here, and a minus sign here, and a minus sign here. And as inquisitive engineers, we ask ourselves, why are there minus signs? And the answer is the same answer that we had for that same question last time. Why is FAZ negative CL? Because Z is down, lift is up. That's the only reason, is that they're in opposite directions. Same thing up here. So I didn't intend it this way, but it's appropriate that I talked about being on a talk show, because I have this in this lecture just because this stuff tends to be kind of dry. This is from Reader's Digest. And it's called The 50 Secrets Your Pilot Won't Tell You, plus what your flight attendant thinks of you. I didn't show this in 514, did I? I don't think I did. I'm sharing this, right? This is interesting, and one of my former grad students, PhD students, flies for American Eagle. And so we've talked about this, and he says, yeah, most of this is true. He's a pilot. So I've highlighted some of the more fun ones. This one's interesting. I'm constantly under pressure to carry less fuel than I'm comfortable with, because the more fuel, the more weight, and the less efficient you fly. Sometimes you carry just enough fuel and you hit thunderstorms or delays, and then you're running out of gas and you have to go to an alternate airport. And that highlights the thing that I always say about airplanes is, versus cars, is if something goes wrong with your car or you run out of gas, you pull over to the side of the road, right? But in an airplane, you can't. You have to find a place to land. Except a former faculty member used to live in Philadelphia, and he said that there was one interstate there in the city where if your car broke down in the left lane and you came to a stop and you're in the left-hand lane, you have 20 seconds to get out of your car and run like mad in front of your car before somebody slams into you. I thought that was interesting. I don't know if I'd have the courage to jump out of my car and go running down the freeway. This one's interesting. We tell passengers what they need to know. We don't tell them that are things that are going to scare their pants off. They won't say, ladies and gentlemen, we have had an engine failure. They'll say, we have an engine indicating improperly. And that's over here, as indicated here as well. And they'll say, instead of saying, oh, wow, it looks like we're flying into a really horrible thunderstorm, they'll say, there looks like there's some weather ahead. Where's that?
On the right.
Down here? Sorry.
Right above you, cursor.
This up here?
No, right here, where it says improper, indicating improperly. Read the.
Oh, yeah. More likely they'll say nothing because you're just going to fly just fine with one engine not working. Which we've studied that condition, right? And we know that it can be problems. Most of the time, how you land is a good indicator of the pilot's skill because everything else is automated. So if you're getting off the plane and you want to compliment the pilot, say, nice landing. They talk about 2 of the worst airports to go in and out of just because of the noise abatement procedures. Washington, Reagan, and John Wayne out near LA. Yeah. And there's another one related to LA. Let's see, where is it? Oh, here. People always ask, what's the scariest thing that ever happened to you? And I tell them it was the van ride from the Los Angeles airport to the hotel. He's saying it's much more frightening to be in the van on the freeway in LA than it is to be flying in an airplane. Yeah. It's one thing if the pilot puts the seatbelt sign on for passengers, but if he tells the flight attendants to sit down, you better know, that something's happening. This is related to the Hudson River landing. There's no such thing as a water landing. It's called crashing into the ocean. And this one is mostly related to, I believe his name is Dean Headley in the business school here. He puts out a report every year about airline quality and rates them on time arrival and departures and comfort and convenience and everything else. And he started dinging airlines for not arriving and departing on time. And so what they did was they adjusted their flight schedules to include some padded time in that departure and arrival time so that they could arrive more often on time. Kind of makes sense if you're being graded on it, right? You want to pad your time. This one, we did this when our daughter was small to save money, but they say riding with a baby in your lap is not a good idea because if there's a crash, the kid's going to go flying, right? Which is why you wear a seatbelt. And I talk about this in 514. I like to sit over the wing because you're on the CG and then you're rotating about the point you're sitting at, as opposed to if you're the tail or the nose, you're going up and down a lot more when you're in turbulence. I've talked about how also there's more crash zone in front of you if you're sitting there, and the wing structure protects you in the event of a crash. But the downside is there's fuel in the wing in a crash. So kind of trade-off. And evidently the studies show that survival rate really isn't real correlated to which seat you're sitting in. It's just pure dumb luck. This is really important now. The general flow of air in any airplane is from front to back. So that is maybe more important for the spread of viruses in airplanes now than it used to be. Although I understand that they've put a lot more air sanitization and they put HEPA filters on the airplanes to try to help out with that. Almost done here. Oh, this is an important thing that most people don't pay attention to. Travel in sturdy shoes, not flip-flops, even if you're going to Hawaii or the Bahamas. Because if for some reason you need to evacuate the plane and you're in flip-flops and the runway's on fire, that could be a problem. Or if you're just going across the runway and there's debris. I didn't even ding this one. It says most people get sick after traveling not because of what they breathe, but because of what they touch. Always, where does it continue? Assume that the tray table and the button to push the seat back have not been wiped down. Hopefully nowadays they are doing that. And a few things that the flight attendant will say. All too common in scenario, I hand you a cup of coffee and say cream and sugar, and you say what? I say cream and sugar, you say what? Come on, people, what do you think we're going to ask after we hand you coffee? Your favorite color? So and this is interesting for pilots. The truth about airline jobs is you don't have as much time off as your neighbors think you do. You don't make as much money as your relatives think. And you don't have as many girlfriends or boyfriends as your wife thinks you may have. Still, I can't believe they pay me to do this. All right, so a little levity and interesting facts from pilots about airplanes. Some of them are relevant to where you sit and choosing how you fly in an airplane. And see, that's where I needed the guy that sits over in the corner and laughs at my jokes, right? I think we'll call it good for today. Oh, notice there's a new homework posted. It's not due. You guys have a flight assignment due in a week. So this is not due until Tuesday the 5th, which is also when we need to have an exam. I think I have the date right. Did I get that right? Is that Tuesday the 5th? I have it here. Let me look. No, the 3rd, Tuesday, November 3rd. And what I'll do is the exam will cover problem number 1 on the homework. And so on the Thursday before the exam and before this is due, I will go over that and give you the answers so that you can spot check your work, so that you will have feedback on it before the exam. No. It's over everything after. It's on the longitudinal and lateral directional trim calculations and